Welcome to lecture 33. In this lecture, we're going to talk about interference and the production of standing waves in sound. All right. So in our discussion of waves, we have talked about what standing waves are. They're just basically waves that are stuck between starting point and finishing point. These two ends are fixed, and as the wave goes and from one end to the other, it reflects back producing places called nodes and antinodes in the phenomenon of interference. All right, creating what we call stationary waves or standing waves because they aren't going anywhere. All right, they're stuck. But there is interesting phenomenon to be studied for standing waves, as we have already seen when I tried to badly play the guitar. However, let's talk about wind instruments and sound. Now, how do wind instruments actually produce standing waves? Let's talk about that because it has important implications when we study sound. Let's say we have a pipe of some length, and you take your mouth and you blow on one end of the pipe. Now, consider that both ends of the pipe are open, so this can be instruments like the flute. If both ends are open, that means at these open regions we have air columns, and you blow into one end of the pipe. Okay. Now think about what's happening. So you're blowing into one end of the pipe with a certain frequency produced by your vocal cords. Let's call that F1, and that frequency is going into this pipe, causing oscillations of these air molecules, right? So it causes oscillations of these air molecules, and this produces different shapes of waves. These are standing waves because they're produced in the middle of air columns within this pipe. Now, when this your vocal cord has a special frequency called the driver frequency. Why? Because you're in essence driving the air columns inside the pipe so that it is producing waves in it. This driver frequency turns out that only multiples of this driver frequency will be produced in this pipe. Okay, only multiples of this frequency will be produced in this inside this pipe as standing waves. This driver frequency is called the natural or resonant frequency. All right. When this driver frequency equals the driven frequency, so since this is called the driver, let's call this driven frequency. So the air is driven by you. So the vibration of air molecules is vibrating in a with a driven frequency. When this driver frequency F1, and let's call this F2, becomes equal to this driven frequency, we have a phenomenon known as resonance. At resonance, natural frequency is amplified. All right. So standing waves produced in these kinds of instruments is technically the amplification of one natural frequency in your from a source, which is oftentimes you're blowing into one end of the pipe. Okay. Since we are only producing multiples of one natural frequency, or multiples of natural frequency of whoever is playing the flute or such kind of instruments. Therefore, only specific frequencies are possible. All right. These are called harmonics or resonant frequencies. Okay. Now, let's look at this pipe in more detail and examine the types of waves we can have. Now, this is a pipe with both ends open, like a flute. Okay, and we're examining the standing wave patterns that are produced. Now, at open-ended pipes, basically the pipe is open to at both ends to air molecules. Okay, so at these open ends, the air is very unruly. So it is going everywhere. So if you take one air molecule here, it's going in all directions. All right. So these regions will always be of high pressure. Therefore, you will always have antinodes at these ends. So at each open ends, for all resonant frequencies or harmonics produced, you will have always antinodes here and here. Okay, since they're open to the air. Therefore, this is the first harmonic, which has antinodes at both ends. And this first harmonic will have for a pipe of length L. If you look at how a cosine wave is produced, this is a basic cosine wave. If I can draw it right, okay, this is a basic cosine wave, and if I look at this wave, this is essentially just half a wave, right? This is from a crest to a trough. So this is just half a wavelength because a crest to a crest is one wavelength. This is just half a wavelength. So this whole length of the pipe for this first harmonic is producing a wavelength length of lambda over 2. So the wavelength is actually twice L. This is the maximum wavelength for any harmonics produced. All right. And corresponding to this, we can find the frequency using the fact that uh, for waves, V equals the frequency times lambda. So frequency is equal to V over lambda. Since lambda is 2L, frequency is equal to V over 2L. Okay, we call this F1, and this is first harmonic or fundamental frequency. Okay, and this is let's also call this lambda 1. This is the wavelength corresponding to the fundamental frequency. The wavelength for pipe with open ends, this is the maximum wavelength produced. And so the first harmonic or first fundamental frequency is the smallest frequency, because as you can see that frequency and wavelength are inversely related. So if lambda is the largest for that case, then frequency should be the smallest. Okay, the fundamental frequency is, or natural frequency, or the first resonant frequency is the smallest frequency. Okay, now moving on to this next shape right here. It is basically a crest to a crest. A crest to a crest means that the wavelength produced is basically equal to the length of the pipe. This is one full wavelength produced here. So lambda 2 turns out to be just L, and corresponding to that we have F2, which is frequency over lambda. Frequency equals speed over lambda. So speed is V over lambda is L. So this is the second harmonic, or um, or first overtone. Okay, whichever one you choose to call it. All right, as you can see that the frequency is F2 is greater than F1. All right, and lambda 2 is smaller than lambda 1. So this because no other wavelengths produced for this pipe can be bigger than lambda 1, and no other wavelength produced for this pipe can be can have smaller frequency than F1. Similarly, if you look at here, this is technically 1.5 wave. So crest, and a trough, sorry, and the lambda 3 is therefore um, the 2 over 3 times L, okay, because L is just 1.5 times lambda. This is the third wavelength, and for that third wavelength, we have the third harmonic, which is speed over the wavelength. If you divide by 2 over 3, it becomes 3V over 2L. Okay, this is the third harmonic. And generally, we can find a progression like we did for waves produced on a string of a guitar or a stringed instrument. The pattern for open pipes, that is open-ended pipes, is the nth wavelength is equal to 2L over n, while the nth harmonic or nth harmonic frequency or nth resonant frequency is n times V over 2L. This is the pattern for open-ended pipes, okay, like flutes. And n is 1, 2, 3, and so on and so forth. All right. Now let's look at what happens if we close one end of the pipe. One-ended or one closed end, one open end pipes are basically the instruments like a clarinet, for example. All right. For a clarinet, we will have this kind of mechanism where one end of the pipe is closed while the other end is open to the air. Now, similar to here, air molecules are unruly, and so at open ends, we always must have nodes, antinodes, all right? And for closed ends, we must have nodes because here the air molecules are not moving, they're stationary. So you'll have zero displacement, and so nodes. And at this point, if I must fix this, this is an antinode, and let's see, change in color, drew it wrong. It's a node there. All right. Okay. Now let's talk about what are our wavelengths and frequencies. For the first harmonic, this is, if you look at the cosine wave again, this is just 1/4 of the wave. Okay. This is from here to here. So the length is just 1/4 of a wavelength, lambda over 4, and therefore the first wavelength is equal to 4 times L. Okay, so this is bigger than the first wavelength for two ends open pipe. Corresponding to that, the first harmonic frequency is speed over lambda, which is V over 4L. This is the first harmonic. Okay, the second harmonic looks like this, and here this is just looking at the shape. This is a node here, antinode here, a node there. So this is half a wave, and then this is another quarter. So quarter and half. Therefore, length is your 3 over 4 lambda, and therefore the second wavelength becomes 4 over 3L. Corresponding to that, we have the second harmonic for one end open pipes, which is 3V over 4L. This is the second harmonic. Okay, just follow along the progression. Here we will have lambda 3 is 5 over, actually 4 over 5, 4 over 5L, and F3, the third harmonic frequency, will be 5V over 4L. Okay, so this is the third harmonic. Similar to before, we can find a pattern here. The pattern that follows along is for pipes with one end open is lambda n, the nth lambda is 4L over n, and 4L over n, and Fn, the nth harmonic frequency, is equal to n times the speed over 4L. Okay, and it turns out, if you can look at the pattern here, F1 was 1 times V over 4L, F2 is 3 times V over 4L, F3 is 5 times V over 4L. So it turns out that n can only be odd. N can only be 1, 3, 5, and only odd numbers. Okay, this is just how it is. For one end open and one end closed pipes, this is the pattern that we follow. Let's call it one end open. Okay. Now let's test our understanding as usual by studying an example. All right. So here we are given that the resonant frequency of a pipe instrument or a wind instrument lies in the range of the audible range. Audible frequency range is 20 hertz to 20 kilohertz. We want to know what is the greatest length of that pipe, considering that, let's say that the pipe is open-ended, so both ends are open. For both ends open, we have learned that the pattern that we know is lambda n equal to 2L over n, while the nth harmonic frequency is n times speed over 2L. Now, largest or greatest length corresponds to lowest frequency. Why? Why? Because an increase in length corresponds to a decrease in frequency. So if you have the length at maximum value, then the frequency will be at the lowest value. As simple as that. Okay. Therefore, what is the lowest value? Lowest value is the fundamental frequency, which is F1. So F1 is V over 2L. If the resonant frequencies for this pipe lies in the range 20 Hz to 20 kHz, the lowest of these resonant frequencies will be our natural or first harmonic natural frequency. This is then equal to 20 Hz. Now then we want to find what L is, so we cross multiply 20 to 2L and V to 1 down there, and we get 40 times L is equal to V. Now what is V? V is the speed of sound. And since we don't have any temperature given, we assume that we're working at room temperature, for which V is around 343 meters per second. Therefore, 40L equal to 343. Divide both sides by 40 to get L. We end up with a length. The maximum length of the pipe is 8.58 meters if the two ends of the pipe are open. What happens if we have one end closed? Okay, for one end closed, we have learned that our pattern is lambda n equal to 4L over n, and Fn is n times V over 4L, and n is selected between 1, 3, 5, so on and so forth. And because these are odd numbered ends. Now, for the same thing goes for the maximum length. We will have the minimum frequency. So the minimum frequency is here F1 as well. So V over 4L, and this is still equal to, for the same pipe, the first harmonic or fundamental frequency or natural frequency, whatever you want to call it, is 20 Hertz. Therefore, in this case, we have 80 times L if we cross multiply, and that is equal to V, which is 343. If you divide both sides by 80, the maximum length that you get for one end closed pipe is 4.29 meters. Okay, so as we can see, to produce the same frequency for an open-ended pipe and a closed-end pipe, we have very different lengths of the pipe. Okay, that's why they are different instruments. All right. Now let's look at interference of sound waves a little bit more closely. Let's look at the phenomenon of interference. We already know from waves theory that when waves are lined up to each other and they interact or interfere, we have constructive interference, which is a phenomenon where amplitude is increased. If the opposite happens, that if the waves are not lined up, rather we have a destructive interference where the amplitude is lowered or decreased or diminished. Okay? In this case, lined up, we have the lined up case, we have the amplification of the wave, and the unaligned case, we have the diminished the result is a diminished wave. Let's say we have two speakers emitting sound and you're at a concert. Speakers are positioned at A and B. You're standing here. Now, what is since there are two sources of sound producing sound waves which reaches you, that means that we will have interference of two different sound sources producing waves which are trying to get to the same ear, right? Let's also say that the frequency is the same for both sources. And let's look at the wave produced by A. Now, again, I'm not saying that sound waves are transverse waves. This is just easier to picture. That's why I'm drawing sound waves as transverse waves. We already know that sound waves are, in fact, longitudinal. Okay? Now, before, if the wave starts from A, before getting to you, A will have traveled through B and then finally got to you. But B doesn't have to travel through a speaker A. It will directly go to you. So we can say that there is a sort of difference between the two waves reaching you. That difference is, we can look at the picture and see that before reaching speaker B, the sound source A, the wave produced by A, already travels one full wavelength before reaching reaching B, okay, reaching the sound source B. And then we have, after this point, we have two waves traveling to you. So these parts of the waves will interfere. Now we can see that the crests of these waves are lined up. Hence, this is a scenario of constructive interference. Okay, because the crests are lined up with each other, the troughs are lined up with each other, and so on and so forth. So this is a constructive interference scenario, and the fact that the wave produced by A already traveled one full wavelength before it interacted with the wave produced by B. This is what we know, what we call as path difference. That is the difference in distances traveled by the two waves that are interfering at the end. Okay. So in this case, the path difference is actually just 1 times lambda, one full wavelength. Okay. And we see that for path difference of 1 lambda, we are having constructive interference since the waves interfering with each other before reaching your ear are lined up, and hence you will hear more sound. Okay, if the two waves interfering look like this with a path difference of 1 lambda. Now, for the same two sources, if the waves produced have shapes like these, then we see that the path difference is not quite 1 lambda, but in fact it is half lambda. So before reaching source B, the wave produced by source A, the green wave, has traveled 1/2 lambda. This is the path difference, okay? And in that case, we see that the second wave produced from the second source, this blue colored wave, we see that these are not lined up. The crest of one wave is lined up with the trough of the other. So this is a scenario of destructive interference. So if the waves interfere with a path difference of 1/2 times lambda, you will hear a diminished sound or a lighter sound, okay, or a lower volume sound. Therefore, this is a pretty general trend, and in general, we can write that for constructive interference of two sound waves from two different sources with the same frequency, if the path difference between the two waves is n times lambda, where n is 1, 2, 3, and so on and so forth, we will have scenarios like this, or constructive interference. Whereas for path difference of n over 2 lambda, where n is 1, 2, 3, and so on and so forth, actually 1, 3, 5, 1, 3, 5, because 2 over 2 will be 1 lambda, which is constructive interference. So it's actually 1, 3, 5, n can only be odd numbers. In these scenarios, we'll have destructive interference. So if you have fractional multiples of wavelength, we'll have destructive interference. If we have integer multiples of wavelength, we will have constructive interference. Now, let's end this lecture with an example that looks at this scenario a little bit more mathematically. Here we have you, say, you're standing at a concert hall in front of two speakers located 2.5 meters away from each other. Let's call the speakers S1 and S2. And you're standing 35 meters directly away from second speaker S2. Now, you notice that if you go up, if you move up or if you move down, then the loudness of the sound reaching your ear actually decreases. So it gets quieter if you move upward or downward. Meaning this at P, this position is what we are calling P, we have maximum constructive interference because the sound is loudest here. If you move up or down away, then the sound decreases. So we have maximum constructive interference at P. Now, this means that our path difference for the two sound waves producing the same frequency sounds, the two sound sources S1 and S2 producing same frequency sounds that reach you, the path difference between S1 and S2 must be n lambda. All right. And at P, because you have maximum constructive interference, that should be the first path difference. So the path difference for which n is 1. At this point, you will have maximum constructive interference. All right. Why? Let's see why we're considering n equals 1. Because we want the smallest frequency for which P is the point of maximum constructive interference, or the loudest point in this arena here. All right. So the smallest frequency must correspond to the largest wavelength, and that occurs when the path difference is 1 times lambda. All right. Therefore, now let's look at how we can solve the problem. So sound waves are produced from S1 and S2. They will interfere before they reach you. So they will travel, this S1 will travel a distance of this in a straight line, while S2 will travel a distance of this horizontally to reach you. Therefore, we end up having a right angled triangle that's looking like somewhat like this, less tilted, but it is what it is. This is a right angle triangle. We know two sides. This is 2.5 meters, while this is 35 meters. And with Pythagoras theorem, we can find that this side is actually 35.1 meters. Okay. Now, what is the path difference? S2 to P is the path traveled by the wave produced by sound source 2 to U, and 35.1 is the distance that sound produced by S1 travels from the speaker S1 to U. Okay, so the path difference is actually equal to the difference of these two paths, 35.1 minus 35, the bigger minus smaller, and this is just 0.1. Now we know that path difference for this kind of constructive interference that occurs at P, where you hear the loudest sound, is equal to 1 lambda. So 0.1 is actually equal to 1 lambda. So the maximum wavelength lambda for which this occurs is 0.1. Hence, the minimum frequency will be corresponding to this lambda, and minimum frequency can be related to lambda using this formula, v over lambda, because v, the speed of a wave, is lambda times f. So frequency minimum will correspond to a wavelength maximum. Therefore, if you use the speed of sound to be 343, the room temperature speed of sound, we have 343 over 0.1. This gives us a frequency of 3,430 Hertz. This is the minimum frequency for which you will have a scenario where P is the point of maximum constructive interference. I hope this lecture made sense. Thank you very much.